Welcome back. We are now going to work on chapter 10, and we will study bound states of central potential. Well, it turns out chapter 10 is really a continuation of chapter 9, where we have established how to solve the problem of a spherically symmetric potential. And we also realized that the two-body problem, so for example, an electron interacting with a proton, can be looked at, can be really considered as a spherically symmetric system in the coordinate system of the center of mass. This is what we have established in chapter 9. We've also established something very important, is that we can use the operator L square and any component of L, so usually LZ, to commute with H and form a complete set of commutating operators. So why is it important? It's important because that means that we will be able to choose all the eigenstates of the Hamiltonian as being also eigenstate of L square and LZ, and we will see that it does indeed make things much simpler for us. So in particular, the operator L, which is the orbital angular momentum, looks very much like its definition, this classical definition that you have studied in your introductory physics courses, with the caveat that we are now talking about operators. So we have the R operator and we have the P operator. And as I just said, we can use H, L square, and LZ as a set of a complete set of operators that commute. That also means that we can write the eigenstate that we are looking for using the labels E, L, and M. E being the eigenvalue of H, L labeling the eigenvalue of L square, since the eigenvalues of L square are L times L plus 1 times H bar square. And finally, M is also a good label because M H bar is an eigenvalue of LZ. So when everything is said and done, we found in the last chapter that the wave function, so remember, wave function is a R representation of a ket. So this is exactly what this is in the box there. So the wave function of the eigenstate of the Hamiltonian is actually can be calculated using the Schrödinger equation that you have there in the box. So why it is important is because we spent a lot of time to separate the effect of the on spherical coordinate, the angular part with the radial part. And this is what we end up with, this very important equation. I'd like to remind you that the first two terms, so the first term between the large parentheses, is the kinetic energy. And the second one is actually the kinetic energy of rotation, L times L plus 1 times H bar squared to 2 mu R square. And I reminded you, and I like to insist on this, that this term turns out that we will use it as an effective potential, which is really a centrifugal barrier. In other words, it's a term that will tend to increase the distance between the two particles we looked at. And of course, that the strength of that interaction depends on the momentum L. So all that makes a lot of sense. And of course, we have at the end V of R. And V of R is a special potential. It's a potential that only depends on the distance between the two particles. So this is why we can use spherical coordinates. So you see, we have to use a lot of tricks and mathematical description just to solve that simple problem of two bodies interacting. So let's spend this chapter here trying to show a few examples that can be solved exactly. That's what this chapter 10 is all about. But before we go there, I'd like to just say a few more words about the angular dependence. And the angular dependence is actually completely obtained by the eigenfunction of the L operator. In fact, these eigenfunctions, you see, they are labeled by L and M because they are eigenfunctions of L square and LZ in this case. Okay? This is important to remember. It is not so important to remember the mathematical shape of each function. I mean, it's easy to find in tables, but it's important to remember the shape, the spatial distribution of them. And it goes from the spherical symmetric system, which we know very well. It's the S state, L equals 0, M equals 0. Then we have P state, L equal 1, M equals 0, and L equal 1, M equal plus or minus 1, and so on and so forth. And so they become more and more complicated as L increases. And why do they need to be more complicated? It's because each of these orbitals have to be orthogonal to one another. So the distribution indeed changes like this. It's also interesting that you always have this donut shape for the largest projection of the momentum, and that also means that the chemistry will be affected by this. We will see that because, of course, we have not spoken about chemistry yet, but when we look at the hydrogen atom, we'll understand this a bit better. Speaking of which, we are going to talk about the hydrogen atom at some point, but before we do that, we are going to look at the radial wave function near the origin. So this is actually what we are going to do in the next few slides, is to show that because of the specific shape of the Schrödinger equation in spherical coordinates for a spherically symmetric potential, because of that, the behavior of the wave function of the origin has a specific form. And to do that, let's try to remember what we do. We have the wave function that's written there, and we know that we can separate the angular dependence, theta and phi, and it's actually obtained by the spherical harmonics y, and then a radial part r. And when we do that, we can replace the whole thing in the equation that we had on the 2 slides ago, and we end up with this equation. And you, of course, notice that we no longer use we use the straight d, since we only have r dependence. And when you look at this equation, that means that the radial part of the wave function has to be calculated. And something that's interesting is that there is no m dependence there. There is no m dependence at all in the equation, which means that we have a degeneracy with respect to m. So a given value of m is 2l plus 1. I'm sorry, there's a mistake on this slide. It should be 2l plus 1, not 2l plus m. We have a degree of degeneracy which is at least 2l plus 1. So this comes from, of course, the spherically symmetric, the spherical symmetry that we spoke about before. Okay. So let's have a look at this equation that we have here. It's actually not a very complicated equation, but we are going to make it even simpler. We are going to write that the radial part of the equation can be written as the u of r divided by r. Of course, we can always do this since we have not said what u of r was, so this is very straightforward. When we do that, we simplify a little bit the first term. In fact, we end up with this equation, which looks even simpler. It's an equation for u. And why is it simpler? Well, it's simpler because it looks exactly like a one-dimensional problem. Quantum mechanical problem. Indeed, if you remember the 1D system, we have a potential plus a kinetic energy, which is minus h bar square over 2m times the second derivative with respect to the position coordinate, plus a potential. This is really what this looks like. And of course, if we are interested in bound state, we also know that the radial wave function r should be normalized. In other words, the integral over the space should be equal to 1. So don't get confused here by the presence of the r square in the first integral. It comes directly from the volume element in spherical coordinates in 3D. This is the reason why we have r squared dr. Conveniently, though, because we define u as r times big R, the integral, the normalization integral for u looks very much like a typical integral if we were using Cartesian coordinates. So we are in good shape. So what happens near the origin? This is the question we have here. And we will assume that v of r is not more singular at the origin than 1 over r squared. And so what do we want to do that for a reason that's going to become obvious in a second. It turns out that in physics, very often, not always, potential do not decay faster than 1 over r squared near the origin. So we are in good shape for that. Okay, if we do that, we will suppose that we have a regular singularity at r equals 0. So this is what we call a regular singularity at r equals 0 if the potential goes as 1 over r squared. And we are going to be able to write a power series around the origin. So we are going to suppose that near the origin, the solution of the problem is r to the power s. And if we have r to the power s, we can use that, we can substitute r to the power s, and we don't know s, this is what we want to determine. We are going to substitute r to the power s in the equation we started with, which is this one. Of course, it is straightforward to show that if v of r is not more singular at the origin than 1 over r squared, that means that v of r is going to look like this for now. I mean, we are going to make simplification in a second. The point is that I can easily make the second derivative with of r to the power s very easy, and we end up with this equation, which is reproduced here. And of course, v of r will be always negligible compared to 1 over r squared. That's what we said before. So in other words, we suppose that r squared v of r will go to 0, because we said that v of r is a regular potential. Okay, so in other words, v of r decays, the faster that v of r can decay is 1 over r squared. So we're in good shape. And then we find that in the end of the day, the equation above, we can just simplify v of r. We find that there is a relationship between the coefficient s, so the power s, and the value L. In fact, we find a possible solution at s equal L plus 1 or s equal minus L. Now, of course, we know it's pretty obvious that we have to discard the solution s equal minus L, simply because in that case we could not normalize the wave function. Okay, we could not normalize the wave function if the wave function behave as 1 over r to the power L. So on the other hand, we can normalize the wave function is L equal L plus 1. Okay, so sometimes people have trouble. They say, well, what about the solution s equals 0? I should be able to normalize things if s equals 0. So the situation there, we might not have to discard s equals 0, which would be a solution here. Well, it turns out we cannot. We can show that here, that if the wave function behaved like 1 over r near the origin, we would find that the kinetic energy, really, the second derivative of that situation, right? Because if s equals 0, then u of r is equal to 1. Therefore, capital R would be u of r divided by r. That's this 1 over r. So we find that this kinetic energy would be a minus 4 pi times a Dirac function, which we cannot have because we would have a singularity of the origin. So that singularity at the origin is not acceptable, and that means that really the only solution we can have near the origin is r to the power L plus 1. So this is how we prove this here. Okay, so suppose now that we are going that u is going to behave as r to the power L plus 1 near the origin, and then that means that the larger the value of L, the farther away the particle will be, right? This is what this means, because if your power gets bigger and bigger, you can see that the value of u increases faster and faster. And this is due to the centrifugal barrier that we had, which was L times L plus 1 over r squared, 2 mu r squared. And of course, that barrier is a repulsive barrier. Okay, so this is coming from this piece here. And the centrifugal barrier, of course, increases with L. Okay, so in other words, just when everything is said and done, we can say that the radial wave function behaves like r to the power L. So remember that capital R is u of r divided by r. So that's good. So what we've done something fairly straightforward. We showed what was the behavior of the radial wave function near the origin. It is r to the power L. Okay, so this is pretty nice. The wave function will always vanish at the origin unless we have an S state. In other words, when L equals 0. When L equals 0, the state will actually not vanish. It will be finite. Okay, so the way to look at this is that sometimes, very often, the best way to understand this is that to look at the full potential, the effective potential, as being the sum of the attractive potential, V of r, for example, and the centrifugal barrier, which is repulsive, as clearly shown on the left-hand side. So when we do that, we have a potential which has a possibility of having a bound state, as we see on the right-hand side. In other words, a particle could be trapped inside the small local well that we have in the potential. Okay, and that potential, of course, depends. The shape of the potential depends on the angular momentum L, the value of the angular momentum, and because the centrifugal barrier increases with the value of L. Okay, so this is the way these things work. So just to summarize this part, we can write this part that I highlighted in blue, in the blue box, as being an effective potential, even though we remember that the second term is really a kinetic energy of rotation. At the end of the day, it really behaves like a potential. So you remember, you have seen this as well when, depending on the reference frame you use in classical mechanics, this is essentially the same thing here. So the physical origin comes from some context, but then you can interpret the result in a different context. But we have to keep track of the physics that you are describing. In any case, the summary of the past few slides is the red box, is the fact that the radial wave function close to the origin behaves like r to the power L. So finally, now we are going to be able to use all the knowledge we have accumulated so far to look at a real problem, a real physical problem, which is the hydrogen atom. It's well known, the hydrogen atom is really the only atom that we can solve exactly quantum mechanically, and we are going to look into this. In fact, you will see that we have done most of the legwork already with preparation for this spherically symmetric potential. We just already worked out the solution near the origin, and now we are going to move on. We are going to look at the solution far from the origin, and then we are going to connect the two results using a power series. We'll see how the quantization of the energy will come naturally from the mathematics here. So let's keep going. Okay, so the Hamiltonian of the hydrogenic atom is given by this. It's a kinetic potential minus this Z square over R, which is the electrostatic potential, the Coulomb potential. So we clearly see that it's spherically symmetric potential. It only depends on the distance. And of course, the kinetic energy only depends on the distance in the P space. Okay, so that means that we can really solve the problem for the radial equation that we have worked out so far. And now we can explicitly change V of R by minus ZE square over R. Okay, so far so good. We know that the solution U of R will look like R to the power L plus 1 near the origin. And we are going to look at the bound state. So in other words, we are going to look at a state that we can normalize that exists outside, that actually is stuck inside the potential, inside the hydrogen atom. In other words, the electron will interact with the proton. They will be bonded to the proton. Okay. So the first thing we usually do is to introduce some dimensionless variables. That's what we're going to do for the distance, rho, and for something that will be used for the energy, lambda. So I invite you to try to show that these two blue boxes indeed represent a dimensionless number. The point is, those numbers, we can use them now in an equation that can be solved mathematically more in a classical way, I would say, because we have an equation which is dimensionless, and we can use tables if we want, or we can solve it like we are going to do it now. Okay, so you see we have rearranged everything. We have a second derivative. We have 1 over rho square and 1 over rho, and an independent component, and we are going to solve this now. So first of all, we are going to look at very long distances. So what happens at very large distances? Well, first of all, you see at very large distances, the centrifugal barrier is going to be essentially inexistent, right? It's the 1 over rho square. And the potential, in fact, will be also, the potential, the electrostatic potential will also be inexistent. So lambda over rho can be neglected when rho is very large. So in other words, I end up with this very simple equation. Again, same thing as we have done so many times before. We have a function which, when we take twice its derivative, we obtain the same function times a number. There is only one kind of function that does that, is the exponential, right? Exponential with a real argument. So the only two solutions are e to the power minus rho over 2 and e to the power rho over 2. Now, here I don't want you to be confused. Clearly, we have to still find what the values of a and b's are. Luckily, we will be able to determine that one of the two values is equal to 0. In fact, b has to be equal to 0, because if the radial wave function behaved as e to the power rho over 2, then it will actually blow up at infinity, and we wouldn't be able to normalize the wave function, right? Because we would have to integrate something that's infinitely large, which means that it cannot be made 1. So that means that in the end of the day, we have to discard the second part, and we find that for the very large rho behaviors, very large rho, we have power e to power minus rho over 2. And if we want to factor in all the behaviors, the one that's close to the origin, which is rho to the power L plus 1, and the behavior close to the far from the origin, e to the power minus rho over 2, we can do that in that general solution. And that solution remains general because we have introduced a function f of rho that hopefully can connect those solutions close to the origin and far from the origin. And once we have determined f, we will be able to solve the problem completely. So you may wonder, why do we do this? Well, we do this because by doing this way, we already factor in the constraint on the boundary conditions for rho, for the values of rho, because rho goes from 0 to infinity. We know that solution, unless f does not behave properly, already behaves correctly, would behave correctly at the origin and very far from the origin. So let's do that. Let's try to realize how we can solve that. So this is what we have now. The problem we have to solve is this one. We have an equation on the left, and we have a proposition of a solution on the right. So what we are going to do, we are going to substitute it. And after substitution, and this is the place where I invite you to pause the screencast and actually show that you get this equation. That's nothing really difficult, a little bit tedious, but not difficult. You end up with the differential equation for f. Okay? Doesn't look necessarily simpler to solve than what we had before, maybe, but this is what we have. Okay? We have that, and it turns out that this is an equation that people know how to solve mathematically. You could look up in tables, but we are going to do it completely so that we understand what's going on. So we are going to try to have a power series solution, which we can do, of course, going from k equals 0 to infinity. Of course, we cannot use any other powers of rho, because if we use negative powers of rho, we would not have the proper behavior at the origin, because we already have the right behavior at the origin, rho to the power L plus 1. Okay, so we can the lowest order that we can add is the zeroth order. If we added, for example, 1 over rho, automatically that wave function will not be normalizable due to the behavior at the origin. Okay, so let's just have a look at what we did in the previous section of this chapter. So we're going to try a power series solution, which is a general solution for the problem, and we're going to see if it is possible to determine this coefficient ck so that f of rho obeys the equation. And if we can do it, then we will be able to calculate the radial wave function for this problem. That's what we are going to try to do. So, of course, everything is exact. In fact, everything will remain exact until the end of this section. We are not going to make any approximation, but so far, certainly everything is exact. If you substitute f of rho into the equation that's for the equation for f, the differential equation for f, you end up with this equation here. Again, good place to stop the screencast and convince yourself. Two things that I'd like to attract your attention on is the boundaries of the sums. You see the first sum started 2 and the second sum started 1. This is important because it turns out that we can start at 2, even though if you do the calculation, you will find that in fact that first sum should start at 0. However, the first term k equals 0 and the second terms k equal 1 do not contribute to the sum, since the sum includes the product k times k minus 1. This is going to become important in just a second. This is the same argument can be made for the second part of this equation. The sum in principle should start at k equals 0. Instead, it started at k equals 1, which is fine because the terms k equals 0 does not contribute in the second sum, since we have a term k. We cannot do the same thing for the last term. Okay? Now, what we have to do now is to make a substitution. And you're going to substitute k by k prime minus 2. And for the first part. And the second one, you're going to substitute k by k prime minus 1. Okay? This is what we do. The dummy variable k prime then can be renamed k. And then you end up with this equation here. Okay, I just explained what it was in words, but clearly you have to do it on a piece of paper to convince yourself that this sum is correct. This is something you have to do for yourself. This is really not complicated as long as you do proper bookkeeping. Okay, so you end up with this equation, which is actually a great equation because we have a sum of some complicated coefficient times rho to the power k minus 1. So we were able to factor out rho to a certain power, k minus 1 here. And of course now, the fact that this has to be equal to 0 for any value of rho shows you that the only way for this equation to be true for any value of rho is for the coefficients to be equal to 0. Okay, this is the usual trick. So this is what we have so far. And the only way for this to be equal to 0 is for this equation there to be fulfilled. So the fact that ck plus 1 divided by ck is equal to the fraction that I have there is actually stating that the term between the curly brackets in the red box have to be equal to 0. Okay? So this is great. We are making amazing progress because we are able to find the coefficient ck plus 1 as a function of ck. And why is it important? Because of course, we don't know C0, if you wish, but that's fine because it's going to be determined by the normalization criteria. Now, is it really true? Are we really all set there? Well, we're not quite all set because the problem is we can look at the behavior of this fraction ck plus 1 divided by ck when the coefficient k is, the sequence number k is very, very large. So we look at this asymptotic behavior. What we see directly from this ratio there on the right hand side is that when k goes to infinity, this fraction behaves as 1 over k. That's actually pretty straightforward to see. Now this is a big problem, it turns out, because this behavior 1 over k is actually the behavior of the exponential e to the power rho. Okay? This is the behavior of the e to the power rho. Now, how do you see this? Well, the best way to see this, which is not very complicated, is to write a Taylor series of e to the power rho. And the Taylor series of an exponential is the simplest one that you can think of. And what you will find is that indeed the ratio between consecutive coefficients does always behave as 1 over k, so 1 over the number in the coefficient. So in other words, the solution we find for ck plus 1 divided by ck correspond to the exponential e to the power rho. But we cannot accept it. Why? We cannot accept it because we already found that the behavior far from the origin should be e to the power minus rho over 2. But if we have e to the power rho times the terms that we already included, e to the power minus rho over 2, we are going to end up with a radial wave function that actually blows up at the for very, very large rho. In other words, we end up with a wave function that cannot be normalized. So the only way that we can avoid this is to avoid for k to go to infinity. In other words, to have this series to terminate. So we have to find a way to for the series to terminate. In other words, at some value of k that we are going to call nr, let's say, the coefficient c of nr will be equal to 0. Once the coefficient equal to 0, all the next one will be equal to 0 as well. And therefore, we will never end up in this uncomfortable situation where k goes to the infinity, because that would correspond to the exponential, which cannot yield a wave function that can be normalized. So it has to terminate, so there must be a value which we are going to call k equal nr, where this fraction over there, up there, is equal to 0. In other words, the numerator will be equal to 0, which means we have nr plus l plus 1 minus lambda equal to 0, which of course gives us lambda equal 1 plus l plus nr. nr is some number, is the largest coefficient in the polynomial that we use f, for the polynomial f, okay? So it's some number, 0, 1, 2, 3, and so on. 1 is obviously an integer, l is an integer. We know that. This is l times l plus 1 times h bar square is an eigenvalue of L squared. So in other words, what we've just done here is to impose lambda to be an integer. So lambda can only take on value 1, 2, 3, 4, 5, whatever. That means that if you remember, and this is written in the blue box, if you remember the definition of lambda, it's some constant, z, e, h bar square, and mu, and the value of the energy. So in other words, the fact that lambda is an integer and can only vary by integer values imposes E to be quantized. E can only take some values. So this is the origin of why the hydrogen atom has very well-defined quantized energy state. Okay? So in other words, what we just found is that we can find a solution of the radial equation, Schrödinger equation, so long as f is a polynomial of degree nr. In fact, this is a polynomial which is known as the associated Laguerre polynomial that you can actually find in tables, and online you can find the plots of them fairly easily. So this is essentially the end of the solution for the hydrogen atom. That's what we've done. We've completely solved it. We, of course, remember that the angular dependence is given by the spherical harmonics, just like for any spherically symmetric two-body problem that we have discussed for quite a bit now, in chapter 9 and now in chapter 10. Okay, so let's try to think a little bit more about this in terms of quantitative argument now. So lambda is equal to 1 plus L plus nr. Since lambda is equal to this value that depends on the energy, we find that the energy has to be quantized this way. Some coefficient, which is a constant, divided by 1 over 1 plus L plus nr squared. Okay? L takes any value from 0 to whatever, to a very large number, any number, and R also goes from 0 to any number. In other words, the 1 plus L plus nr can be written as n, which goes from 1 to infinity by values of 1. So we can write it this way. We're going to call n the principal quantum number. Why could we call it that way? We call it the principal quantum number because it's a number that completely provides the value of the energy, and we end up with this important equation there, which is of course well known. This is the spectrum of the hydrogen atom. Okay? And we can of course plot it this way, and we find that if we plug in all the numerical values within the equation from the previous slide, we find the energy or the different state depend on n is equal to minus 13.6 eV times n squared, divided by n squared. So this is quite different from what we saw for the harmonic oscillator, where all the states were equidistant. Now the states actually go down, the distance between the state go down as 1 over n squared. And what's very important about this is that we can measure the distance between the different states by doing an excitation, for example, an electron from E1 to E2, and then we let the electron relax back into E1, and then we can measure that, and so we can test this model. Okay, and this is the way it's done. Is here is just a distance between two states. Of course, when an electron relaxes back to a lower state, in the ground state, for example, it emits some photon, which correspond to the difference in energy, and that photon can be measured, and then the energy can be measured. And we end up with this. This is a 1964 plate from spectroscopy that clearly shows these different states, and they actually go as 1 over n squared. So that was a beautiful demonstration of the power of quantum mechanics to understand one atom completely, to understand it very well. Well, we know it's completely understand, but we'll see that as the experiment improved, there are some features in there that have not been described. But we will, of course, describe them actually in next chapter. Okay? So before we move on, I'd like to talk about the hydrogenic wave function. Remember, we have the wave function, we have the radial wave function. We just found that they were related to the Laguerre, associated Laguerre polynomial. And then we have the spherical harmonics. And then we can find that, of course, we can just now plug in all the numbers that we found for the energy and find and then plug in back the value of rho as a function of r. And in particular, we find that the different state will have a very specific behavior. For example, the ground state wave function, which is n equal 1, and for which L has to be equal to 0 and nr equal to 0, will look like C0 rho e to the power minus rho over 2. And that means that with the normalization and taking into account the radial wave function, we find that the wave function for the ground state behaves like a decaying exponential, as provided here, with a typical length scales A0, which is called the Bohr radius, which is 0.529 angstrom, which is only depends on constant of nature, and of course the mass the mass, the reduced mass between the proton and the electron. So this is the way the wave function looks like. It's of course zero angular momentum. It has L equal to 0, and it shows really that even if you don't have an angular momentum, you can have the ground state. And remember, Bohr's model was actually was very exciting model for the atom, because it could explain the quantization of the energies, but it was actually wrong, in the sense that if we remember in this blue box, in the Bohr model was about quantization of the angular momentum. But even if there is no angular momentum, like the zero angular momentum state L equals 0, this is a state that can be explained by that this is a state that belongs to the spectrum of the hydrogen atom. In fact, this one is the ground state. Okay. Now we can keep looking at other states, like the first excited state. There are two ways to get 1 plus L plus nr equal to 2. Can L equal 0 and nr equal 1, or L equal 1 and r equals 0, and we find different states. We always like to remember that nr is actually the number of zeros, the number of times the wave function will cross the x-axis. So that's the number of zeros. This is the order of the polynomial. This is the degree of the polynomial. You can keep working on larger excited states. So if you look at n equal 3, you have many possibilities to get n equal 3. You can have L equal 0 and r equal 2, L equal 1 and r equal 1, L equal 2 and r equal 0. Plus, remember, there is also the degeneracy with m, because m takes any value between minus L and L in each case. So you can see that the degree of degeneracy goes up very fast for all these different hydrogenic states. This is coming from this is a mixture of accidental degeneracy that we will talk about a bit more in the last slide of this screencast, as well as spherical symmetry. So the spherical symmetry comes from the fact that we have all those properties that do not depend on L, actually on M, sorry. In fact, we didn't have any M dependence on the energy, and we didn't even have any dependence on M for the Schrödinger equation, for the radial equation. So clearly, this is a degeneracy. Okay? Now, we can, of course, now that we know the wave function, the radial wave function, we can do integration in spherical coordinates, which includes, of course, the volume element in spherical coordinates, which is a little bit more complicated than in Cartesian coordinates. But we can certainly do that. And if we integrate, if we are very often interested in the probability of finding the electron between r and r plus dr, in this case, in spherical coordinates, we have to consider a shell that is considered between r of radius r and a shell and a sphere. The distance between the sphere of radius r plus dr and a sphere of radius r. So we're interested in having the probability of finding the electrons in that shell that's in between those two spheres. So that means that we have to integrate over all the solid angle sustained by theta and phi. This is the usual trick that we use. And so when we do that, it turns out that that probability, this can be a bit misleading. So this is the right-hand side of this slide, of the plot. The maxima do not show exactly the same place because we are actually multiplying the radial wave function by r square. The r square comes from the fact that we are integrating over all the solid angle to get the result. So this is something that that comes from of course from the fact that we are using spherical coordinates. So we can finally consider where are the peaks, and the peaks can be found by simply looking at the maxima of the square of the wave function. So we can find maximum by looking at the first derivative, of course, and making sure it's a maximum and not a minimum. And we find that the different maxima, when we do this calculation, we find the different maxima are positioned at r equal to n squared a0 divided by z. So for a hydrogen atom with z equal to 1, so we just have one proton, r goes as n squared times a naught. Okay? Don't be confused by the fact that it doesn't look like it's going like n squared times a naught in the plot on the right-hand side, because you should notice that the scale of the x-axis is changing from plot to plot. Okay? If you were using the same scale, you will actually graphically see that the maximum moves up as n squared. Okay, so that's really nice, because that means that we have those different shells of electrons positioned differently in different shells coming from the center of the nucleus of where the proton is located. Now, before we wrap up this section, which is the largest section of this screencast, but we'll keep moving on the other example we can solve exactly, I'm going to talk about degeneracy. So that means that there is a certain number of states which correspond to the same energy, and yet those states are separate states. So let's have a look at them. So for each value of n, of course, we know that there are different values of L, because we remember n is equal to n1 plus L plus nr. So we just find any combination of L and nr that gives us appropriate n. So we know that. This is degeneracy. For each value of L, there is also 2 L plus 1 values of M. This is what we have described when we studied the angular momentum operators. So if you look at the different states, the ground state actually has no degeneracy unless we include spin, which actually includes twofold degeneracy. when n equal 2, we start to increase the degeneracy significantly, especially that the p states actually threefold degenerated. Then we keep going like this, so we have larger and larger degeneracy. In fact, we can calculate the total degeneracy by summing over all the possibilities of having the realization of a given energy. And that is, of course, given by the sum from L equal to 0 to n minus 1 for a given n of 2L plus 1. This is a simple series that we can calculate, and we find that the degeneracy of each state is in fact n squared. If you include the spin, it's going to be 2n squared. So the degeneracy goes as n squared. This is a mixture of accidental degeneracy and of rotational degeneracy. The accidental degeneracy comes from the fact that the potential we are looking at goes as 1 over r. We will find this similar accidental degeneracy for the three-dimensional harmonic oscillator, and we will discuss about the origin of the fact that we have this accidental degeneracy, as I said in the last slide of this screencast. So now that we are done with the hydrogen atom, at least for now, we are, because we will investigate the hydrogen atom a bit more in the next chapter as well, for corrections to the spectrum that we looked at. There is another system that we can study almost completely analytically. This is the finite spherical well. And the motivation to look at the finite spherical well is that it's actually a very good approximation for the deuteron system. So the deuteron system is this combination, this interaction between a neutron and a proton. So this is the nuclear force in the strong interaction variety of the nuclear force. And what we know about that interaction is that it only manifests itself at very short distances. So this is sometimes we say that the particles only interact when they touch each other. This is of course no classical equivalent, because the interaction here is between a charged particle, a proton, and a neutral particle, a neutron. So clearly there is no electrostatic interaction, and there is no other interaction that are, I would say, classical interaction that we would see in everyday life. So we could try to find a model for the interaction deuteron. So here what we are going to do in this section is to use a combination of what we know from experiment and what we know from theory, and try to come up with some model. So this is not exactly what we call a first principle study. So a first principle would only use quantum mechanics and only constants of nature. Instead, it's kind of a combination of the two, so that we develop an understanding, at least a pragmatic understanding of this strong interaction in nuclear physics. So let's get going. The potential that we want to look at is going to look like a square well, which is a little bit confusing always, because when we plot the potential in spherical coordinates along the r axis, indeed the potential looks like a square well. It's what's shown on the left hand side. Of course, this potential in spherical coordinate is a spherical well. So the square well is actually spherical. So this is one of those interesting things that confuse this student. The square well in 3 dimensions is actually spherical. So the idea of this well is that there is no potential above a certain distance a, and there is a potential minus V0 under the distance a. So a, of course, is going to be found to be very small. This is what we mean by strong interaction at a very, very short distance. And we'll find that V0 is actually fairly large. It's a strong interaction. So let's have a look. Let's study this here in this section. We know experimentally that there is only one bound state. One bound state means this. That means that there is an eigenstate of the Hamiltonian corresponding to this system that is right below 0. Right below 0 means there is not enough energy to go over the potential barrier. Okay? That also means that if we try to excite the deuteron atom, we cannot. We automatically dissociate the neutron and the proton. This is what is found experimentally. Okay? So all the excited state will be unbound. And we are going to use that information later when we want to find what what acceptable values of A and V naught can be possible for this model. Okay, we also know that the ground state is an L equals 0 state, which is actually going to simplify our life quite a bit, because the centrifugal barrier is 0 in that case, right? You remember the term L times L plus 1 divided by mu r square, that term which comes from the kinetic energy of rotation, which we also call the centrifugal barrier, is 0 for L equals 0 state, clearly. Okay, so let's try to see what we get from here. The equation we end up with a fairly simple equation, it turns out, because the centrifugal barrier disappear. And in fact, it's even easier when it's away, when it's larger than A, when the distance is larger than A, because in that case, there is no potential. So the second equation is just the free particle equation. You only have the kinetic energy on the left-hand side and the eigenvalue on the right-hand side. And the first equation inside the well is simply an equation with a constant potential V naught. Okay? Now, we already know that we have a finite potential. This is what V naught is. So if we have a finite potential, that means that we will have to connect the solution of those two equations at the boundary, but we will also have to connect the derivative. So remember, this is something that we did, I believe, in chapter 6, where we showed that by integration, we found that if a potential is finite, the first derivative has to be continuous. This is something that we proved formally as well. This is always a good thing to remember. This is one of those things that become a mystery to some students because they forget that's actually key when we try to solve the problem with boundaries like this. Okay, so let's move on and try to solve those two equations, and then we'll connect them, and then we'll see what we get for the energy E. Well, the two solutions will be found by rewriting the equation slightly. So the two equations from the previous slide will be written again by these two equations on the top left. And here, remember that we are talking about bound state, and we are talking about states that are, of course, higher than minus V0, right? I mean, the energy has to be minus V0 and E, clearly. Otherwise, the wave function would be 0, and that means not normalizable, therefore could not exist. So, E is larger than V0. That means that V0 plus E is a positive number. So, we are looking at the first equation in the box there. That means that that number is positive, so we can replace it by K0 square. In fact, K0 square, for K0 being a real number, K0 square will be always positive. So we can certainly replace K0 by square root of 2 mu over h bar square times V0 plus E, which is strictly positive. Okay? Okay, so that's good. The second equation, outside of the well, this is a different story. Because, of course, the energy has to be negative. This is a bound state. This is what we decided to use. It's a bound state. Therefore, we can replace minus E by Q square. Okay? Or actually minus E times 2 mu over h bar square. So you see the difference between these two equations is that there is a minus sign in one case and there is a plus sign in the other case. And by now, you should get familiar. You should know what it means physically. Physically, it means a lot. Physically, it means that the first equation would yield a sinusoidal, so an oscillating solution, while the second equation will give you an exponential solution. And all this is due to the minus sign, because the second derivative will actually will involve the product of I times I, which is minus 1, of course. Okay, so you see this, and you find a solution indeed, that the oscillatory inside the well and the exponential outside the well. Of course, we can already, so this is the solution we have from the previous slide. Of course, we can already know that by normalization, the D value should be 0, because otherwise the wave function would blow up at infinity, so we could not normalize. And we also have established before, for every central potential, so spherically symmetric potential, that the value of U at the origin should be equal to 0. We've established this, and this is also something we establish in the first problem, in the problem set at the end of the chapter, This is also something that we established, that u0 has to be equal to 0. Therefore, the cosinusoidal solution has to be to vanish. In other words, b has to be equal to 0. So we good. We only end up with this solution here. We still have a and c to determine, and of course k0 as well, k0 and q. In fact, we have still quite a number of parameters. Of course, k0 and q are related because they only depends on the energy, and one of the two coefficients a and c can certainly be obtained by normalization. So the rest of the information we need to establish the value of the remaining variables will be the continuity of the wave function at the boundary, at the continuity of the first derivative, and that's what we are going to do now. So this is it's exactly what I just said. In black marking here, we have to find a u that's continuous and its derivative to be continuous as well. So this is what we have, okay? This is just to summarize what we have so far: solution outside of the well and inside of the well, and we have to connect them. U has to be continuous. That means that at the boundary, the solution have to match. This is what's written there. And of course, the first derivative have to be continuous. So therefore, we also have the derivative have to match. And of course, when you do that and we divide the two equations one by another, that allows us to get rid of a and c, we get directly that the tangent of k0 times a is equal to minus k0 over q. And this is an equation that we find quite often. And if we find the solution, and we know that this equation cannot be solved analytically. This is a transcendental equation in k0. So we have now to think about how to solve this. And we usually do this graphically and then numerically. So this is essentially where the exact solution, analytical solution, ends. And now we are going to have to use some tricks, graphical tricks, and this is what I'm going to do in the next slide. Okay, so let's rewrite QA equal eta and K0A equals zeta, and then we end up with the same equation in green. So the equation in the green box is the same as the equation in the red box, but with a change of variable. And there is something else that we have to remember, is the definition of Q and K0. Remember, as we mentioned before, Q and K0 are related, right? K0 was the square root of a constant times e plus v, 0, and Q was essentially a square root of minus e, right, times a constant as well. So the two equations are related. In fact, you can show that in a very straightforward manner, in fact, that K0 square a square plus Q square a square will be given a value 2 mu v0 over h bar square. And when you do that, actually over a4, and this is how the a square comes up. Anyways, I invite you to go 2 slides back and substitute the value of Q and K0, and you will find that zeta and eta are related by this equation. This is simply because we have the definition that we started with to write the two equations inside and outside the well. Okay, so this second equation there, of course, if I were to make a plot of with the x-axis zeta and the y-axis eta, or the other way around, this second equation in the green kind of box there, green color kind of box there, we show that this is actually the equation of a circle of radius square root 2 mu v0 a square over h bar square, right? The other equation, of course, is some eta is equal to zeta cotangent zeta, minus zeta cotangent zeta. Again, if we plot this equation on axis on the x-axis zeta and the y-axis eta, we can also plot this. And in fact, we end up with those curves right here. We find a number of circle of radius, as I said, r0 square given by what's written in the yellow box, and then we have the other equation as well. Okay, so of course we only have the positive zeta and the positive eta for obvious reason, because Q and K0 are positive and A is positive. And of course we need to have those two equations to be true at the same time. And that means that the only thing that we can do here is to get the solution where the curves overlap, so when they cross. And we see that we have a number of solutions there, and this is what we are going to do. So we already know that we will not have any bound state unless the radius is large enough. So you see the first curve zeta cotangent zeta start at pi over 2, right? It started at pi over 2, that's what you see on the bottom left. That means that the radius has certainly have to be larger than that. If it were not, there would be no bound state, no possibility of bound state. That's one thing. So we certainly need that. And we would have one bound state if in fact the value of the radius again is smaller than 3 pi over 2 square. And this is also coming from the fact that this comes from the fact that again we would have too many solutions if the radius was actually larger than 3 pi over 2. So this is something again that we find from this, and we hope that we'll be able to solve for the equation using these conditions. Okay, so far we actually need to know more information from experiment. And experimentally what happens is that you can disintegrate the deuteron, so it's written by D, by shining a gamma ray, a gamma photon to it. And then when you do that, you get enough energy to dissociate into a neutron and a proton. And of course, the energy you need will be exactly the energy of the bound state. So experimentally, this can be done. And when you do that, you find that the energy you need to dissociate the neutron and the proton is 2.2 MeV. So in other words, the eigenstate has to be equal to minus 2.2 MeV. Okay. All right, very good. Now, that means, okay, we also have that formula that we need. And we know that, of course, this is the only thing that we found so far. We found that you remember the radius of the circle has to be larger than something, but smaller than something. Otherwise, you would have no bound state or you have too many bound states. So we can determine V0 and A separately. So let's try to think a little bit what we are trying to do here. We came up with this model for the deuteron system, and we realized that this model we have is not sufficient to understand everything from first principle. Instead, we can only determine V0 and A at the same time, right? This is what this equation is. We only have one equation for two unknown V0 and A. So, of course, that means that we need more experimental input, and the experimental input we could have would be the size of the deuteron, which can be obtained from a scattering experiment. So you see the value of A is 1.7 10 minus 13 centimeter. This is tiny. This is 1.7 10 minus 15 meter, which is actually what we call the femtometer. It's very small. Okay, it's 5 orders of magnitude smaller than the radius of the hydrogen atom. That means that if the energy is almost at the top of the well, so it's barely bound state, we can find that the only solution that's possible is when the radius of the circle I showed before is pi over 2. And we find that the depth of the potential is about 35 millieV. So this confirms that the potential here is really deep. 35 millieV is a very strong interaction. Remember the interaction, the ground state for the hydrogen atom, the electron in the hydrogen atom was minus 13.6 eV. So this one is, again, more than 6 orders of magnitude larger. So this is a very strong interaction. This is why we call it the strong interaction. And one thing that you don't want to be confused about again is that even though the bound energy is minus 2.2 EV, mega EV, the potential well is much deeper. Okay, so when somebody asks you what's the interaction in the deuteron atom, I mean the interaction is really 35 millieV in this model. It's not 2.2 millieV. 2.2 millieV is the energy of the bound state. Okay, good. Before we wrap up this section, just a few remarks that we need to make. if we didn't calculate the wave function, I mean, we did calculate the wave function, in fact, and the fact that we have so close to zero, the energy, the eigenstate is so close to zero, means that there is a very long tail. Well, if you can look at the length of the tail is related to 1 over q that we calculated before, and if E is very small, 1 over q is going to be very large, meaning that there is a very long tail where the potential is 0. So that's what we have. Now, I have to say that this model is great to explain things, but it's not perfect. In fact, the deuteron is known to have an intrinsic spin of 1, even though we didn't include any spin interaction. So clearly, we would need to have we need to find a potential that should be spin dependent. And finally, it turns out the deuteron is not spherically symmetric. It does have a quadrupole moment, which we wouldn't have if it was spherically symmetric. So clearly, this model is a little bit rough, but it's actually good for qualitative and almost semi-quantitative studies. Now that we have established that the interaction between a proton and nucleon can be semi-quantitatively described by this finite spherical well, let's try to see what happens when we put many nucleons together, and then how this strong interaction will actually affect the interaction between the different particles. And this is going to yield the infinite spherical well. Okay, so the idea is we are going to follow here is a Fermi gas model. In the Fermi gas model, we are going to consider many nucleons in a heavier atom. And this is what we call in the field, we call that the interaction we'll look at it, we'll call it the mean field approximation. And the mean field approximation means that each nucleon moves independently in a potential due to the average of the interaction with all the other nucleons. So we do not look at the interaction between each individual nucleons. Instead, each nucleon interact with an average value from all the other nucleons. Okay? We will suppose the potential will be spherical, which again is an approximation, but is the best we can do at this stage, at this level. And of course, the size of the well, so when we say the size is the value A, is going to increase with the number of nucleons. I mean, they need more and more space to be placed, and of course, they interact in a larger and larger distance. Okay? So that also means that if we increase A, we also increase V0 because there is the stronger and stronger interaction with the different nucleons, which means that a very good approximation for this system will be to look an infinite spherical well, because V0 is going to increase very quickly, and that means that we suppose that V0 is very large, and an approximation would be to use V0 infinity. And we'll see at the last slide of this section, we will see how good this is compared to experiment. But at least it's going to give us some very good insight of what's going on in a nucleon. So of course, we are going to look at the infinite potential well, which is of course 0 outside of the boundaries and infinite inside. That means that if we now go back to the radial wave function, and this version here is the version with capital R, not the version with small u. That means that's the reason why we have the appearance of the first derivative as a second term. And we will accept solution that have L different from 0. That's the reason why the centrifugal barrier shows up again here. This equation in the box actually has no potential in it because simply the equation will be inside the well, and where V is equal to 0. Now, the presence of infinite potential outside of the well will actually be reflected in the when we impose the boundary conditions at the edge of the well. And the only boundary condition we have at the edge of the well is for the wave function to vanish. Indeed, it has to vanish, and it has certainly have to vanish when the potential is infinite, which means that it has to vanish at the boundary. Now, if we remember the proof of why the first derivative had to be continuous, we remember it was true because the potential was finite. When the potential is infinite, the first derivative does not have to be continuous, and in fact, it is not continuous. It cannot be continuous in that case. So we end up with that equation to solve, and we can, of course, use dimensionless quantities, as we like to do, and the main reason why we do that is because then we end up with equations that mathematicians have solved for us in the past. So this is what we have there with that equation, which is known actually from textbook in mathematics, or special function. This is a spherical Bessel equation. Spherical Bessel equations can have solutions either spherical Bessel functions, which are regular at the origin. This is the one we like. And I should also note, we can also have the spherical Neumann functions, which turn out to be irregular at origin, and we don't want to, we will not consider that solution because this is not physical. Okay, so this is a good place for me to introduce you this NIST special function website. It's an amazing website. It's actually a project that has been completed recently, and they keep updating all the time. This is essentially the Bible of special functions, a very large number of special functions, graphical representation, properties, many properties, solution of differential equation, derivative integrals. I strongly recommend that you go there, especially if you're interested in special function. This is freely available. This is a government project from the National Institute of Standards and Technology. This is really very good website that I really encourage you to go. So our problem of the infinite spherical well, as we saw, so it's a square well, but it has a finite extent in distance, finite a. We find the solution will be the spherical Bessel function and the spherical Neumann function. That's what they look like. That's what you have right here. Again, we're not going to worry about the Neumann function in our case. We will look at the Bessel function. So what we have not done yet is to impose that the function has to match, has to be 0 at rho equal a, r equal a. Before I move on, I'd like to attract your attention to the fact that when the L equals 0 state for G naught, we find that we actually have a finite value of the wave function at the origin, which is not the case for the other one, which is 0. This is very much reminiscent of what we've seen for the hydrogen atom, where only the state S equals 0, so L equals 0, so the S state was actually finite at the origin. So this is kind of a universal property that we find for this spherically symmetric solution. Okay, so now we still need to show that we can show, and by the way, these are the solution for R, for big R. So that's perfectly fine for big R to be finite at the origin, since U is going to be 0. Since remember, U of R is obtained by R times small r. Okay. Anyways, we need now to impose the fact that those Bessel function have to be 0 at R equal a. And that's going to give us, and since Ka is equal to rho, that will impose a condition on K. And of course, since K depends on the energy, that's going to give us a condition on the energies. In other words, we will find the energy eigenvalues of the problem. This is the way we usually solve these problems. Of course, for the infinite well, we can do this analytically. And then we find that the solution is going to be the different energy will be obtained as h bar square k square over 2 mu, which is looks exactly like a free particle energy, which it is inside the well, right? But the difference being that only some values of k's are available. So a free particle solution will be h bar square k square over 2 mu, but with k taking any values. But because the particle has to stay in the sphere, right, since it's infinite the potential is infinite outside the sphere, this means that only some value of the momentum is acceptable. This momentum will only accommodate the wave function inside the potential well. And in fact, these values of the momentum are obtained by n times pi over a, n taking any value from 1 to infinity. You will also notice that the solution n equals 0 is not acceptable. Okay, so this is what we end up with. These are two examples of three states, sorry. And we can find all the zeros of the Bessel function. Some of them, of course, let me go back to this slide here for a second. Some of them will simply be for G0. We find that the zero of that equation there will be obtained by k is equal to different values of pi, right? Pi, I mean multiplication of pi. That's going to be. We can also do the same for when L is not equal to 0, but we have to do that numerically, so it's not so simple. So you will see here that if you look at this table here, this is going to give you all the zeros of the Bessel function. That means that these are all the possible eigenstates of corresponding to the eigenfunction. You will see on the first column there that for L equals 0, just like we showed in the previous slide, the zeros will be at pi, 2 pi, and 3 pi. And then all the other solution will be obtained numerically. Okay? So all the zeros there are the values of k's that will work out, that will actually give us the right boundary conditions. This is something you can find on the NIST website I showed you before, but also, of course, on the Morse and Feshbach book, which is used to be for decades and decades the Bible. And in fact, there is a one-to-one correspondence between Morse and Feshbach and the NIST website I showed you a few slides ago. So now if you plot all those energy levels corresponding to the values of k's, you'll see that there is an interesting evolution of the different states depending on the L values. And what's nice about this now is that we can build a nucleus by putting a certain number of nucleons. So before I do that, I should tell you that each state that I showed on this picture here actually has a double degeneracy. Double degeneracy because we can nucleons being fermions, they have a spin 1/2, so we can put a spin 1/2 and spin minus 1/2 on each state. So we can put two particles, so two nucleons on each state. I also would like to open a parenthesis here to tell you that we are treating nucleons, proton or neutron, on an equal footing here. We do not make any difference between them. For our purpose, there is no difference between them here. Of course, there are differences, but for this model, we do not have to worry about differences. This model is actually a mean field approach where we don't have to worry about those details. Of course, nuclear physicists worry about these details a lot, but we don't have to worry about them in this context here. So we can build the nucleus, and this is what I did on this state. I've written in red the degeneracy of each state, okay? But by now you should be familiar with this. The first column are L equals 0 states, so I have a degeneracy of 2, right? Spin 1/2 and spin minus 1/2. Since these are L equals 0 state, there is the value of m's that m can take is only m equals 0. For the state L equal 1, we can take m equal plus 1, m equal minus 1, m equal 0. So that's 3 states. Each state can be occupied by a spin 1/2 or spin minus 1/2, so that's 6 states, and so on and so forth. So you have all these different states that you have. And what we see is that you actually start to fill up some shells, okay? And this is what's very important about this model, is that it predicts something that's actually very important. And I see here, this is the same plot but a little bit larger. We see that we can fill the first shell, okay, the state L equals 0, and I'm going to have 2 particles. The second shell I'll have 8 particles. The third shell 18, 20, 34, 40, 50, and so on and so forth. When we fill those shells, the system is stabilized. So filling these shells completely is stabilized. In other words, those numbers should be magic numbers. They should correspond to abundant nuclei. So they are called, in nuclear physics, they are called magic numbers. And I'd like to attract your attention on something. I'd like to remind you the models that we've used are very simple models. And yet, this model can predict this magic number. So the possibility of having nuclei, so in other words, chemical elements that are more abundant than others. And in fact, if you were to do the full calculation, including spin-orbit coupling and spin interaction, you would find that the actual magic numbers are slightly different than the ones that we established here. because we don't have a full model, but the strength of the model we have here is that we do predict the existence of those magic numbers, which is kind of a very nice achievement, given the fact that we spent about 15 minutes on this description, which is pretty nice to understand such a fundamental fact about nuclear physics. Okay, so in fact you can go further. We can go further here. This is the description of different models. It's a lot of data here, but let's not worry too much. The very central one, the second one, the second column is the infinite square well. This is what we just did. Okay, this is what predicts the different numbers that we have. This is what we have there. Now we can also use harmonic oscillators, which is not as good as infinite square well. Then we can say, well, it's not quite infinite. That's going to shift everything a little bit and also create some degeneracy, some degeneracies across the board. And then we can improve this. We can add spin-orbit coupling. We can have square well that have rounded edges. And at the end of the day, we obtain a very good model. The problem is adding spin-orbit coupling is a little bit hard and a little bit beyond the scope of this course, but clearly it include a correction to what the infinite square well does. Actually, I should say that the spin-orbit coupling will be studied in the case of the hydrogen atom in the next chapter. So stay tuned. You will see how things can change when you take spin-orbit coupling into account. Okay, now it's time to move on to the last part of this chapter. So this is a very rich chapter. As you know, as you have seen so far, this chapter has built a lot on what we learned in the chapter 9, where we essentially demonstrated generalities about the spherically symmetric potential. And now we have looked at a number of problems that can be solved analytically or almost analytically all the way to the end. We did the hydrogen atom, we did the finite well, we did the infinite well. And now we are going to study something else. We are going to study finally the three-dimensional isotropic harmonic oscillator. So before I get started, maybe I should tell you what is an isotropic harmonic oscillator. Well, it's an oscillator that is described by this equation. You see the potential is omega square r square times u over 2. And it is isotropic in the sense that you can look at this system as being three springs along x, y, and z direction, with a common frequency omega. Common frequency omega means that the force constant will be the same in all directions, and this is the reason we call it isotropic. So same properties in different direction. That's what isotropic means. Okay, good. So we can write the Hamiltonian in, we're going to first start in Cartesian coordinates, so we can write the Hamiltonian in Cartesian coordinates. This is a fairly simple Hamiltonian, and it turns out it's p squared over 2 mu, which is the kinetic energy, plus 1/2 mu omega square r square, which is this potential energy in 3 dimensions. So what matters here is the distance from the origin, it's r square. We can develop p square as px square plus py square plus pz square, and likewise for r square equal to x square plus y square plus z square. What's important though in this equation is the notation. Look, we have a hat symbol everywhere. We are talking about operators. So these are no longer numbers, these are operators. It means that to solve this problem, we need to find the eigenvalues of the Hamiltonian, therefore the eigenvalues of the operators that we are talking about. This is the job we have to do. Now what we find, something very interesting about this, is that the px and the pxx, pyy, pzz are completely decoupled. There is no cross terms. So in other words, we can write the Hamiltonian as the sum of 3 Hamiltonian, and it looks, for all practical purposes, that this Hamiltonian of the 3-dimensional harmonic oscillator is just the sum of 3 Hamiltonian of 3 independent harmonic oscillators, one along x, one along y, and one along z. This is exactly what's written there on this slide. So that's going to make our life easy, because that means we could probably solve each term separately. Okay? And the only reason we can do that, is because the different Hamiltonian do commute. Okay, remember, if they commute, that means that we can find eigenstates that are eigenstate of the two Hamiltonian at the same time. And if we can find eigenstates that are eigenstate of the two Hamiltonian at the same time, that means that those eigenstates will also be eigenstate of the full Hamiltonian. Of course, because we also have hx and hz commuting and hy and hz commuting as well. So that's a very important result. If they did not commute, that we could not do this, right? Because the eigenstate would not be common to all the different operators. So that means that we can write the energy eigenstate, so in other words, the eigenstate of the full Hamiltonian, using three labels, each being the energy of the oscillator along x, the oscillator along y, and the oscillator along z. And in practice, what we write is the eigenvalue problem can be written just like in the second line on this slide, where we have the sum of the three Hamiltonians, and they correspond to the sum of three eigenvalues because we chose the eigenstate to be eigenstate of the three operators at the same time, and the total energy of the system. So in other words, the eigenvalue of the full Hamiltonian is simply the sum of the energy of the three oscillators taken separately. That's what we find. That's actually pretty straightforward, but it's sometimes good to do it in details to convince yourself. The good thing, though, is that we do know the eigenstates that correspond to an oscillator in one dimension. We've studied it in the previous chapter. In fact, we studied in detail. We find that the energy was obtained by n plus 1/2 times h bar omega. So instead, here I use the notation nx and y and nz for the n along the different directions. And because we have an isotropic oscillator, all the omegas are the same for all the three oscillators. Therefore, we can write that the total energy of the system is nx plus ny plus nz plus 3/2, okay, times h bar omega. So one thing that's interesting, of course, because nx and y and z can take on any value between 0 and in fact infinity by jump of 1, so they're integers, we can write that the energy of the three-dimensional harmonic oscillator is n plus 3/2 h bar omega. So what's very telling is the 3/2. You remember we saw 1/2 for one-dimensional harmonic oscillator. You would have 2/2 for two-dimensional harmonic oscillator and 3/2 for a three-dimensional harmonic oscillator. So basically that number tells you the dimensionality of your problem. That's kind of interesting that the energy will depend on this, and of course this is the 0-point energy in a three-dimensional harmonic oscillator. Okay, so that's what we find. This is a fairly easy problem to solve, really, because we are just using information that we knew otherwise from a different context. So let's try to see if we can go further than this. And before we go further than this, we are going to look at what the eigenstates look like. So that notation that I have on this slide is basically saying, what is the wave function? What is the xyz representation of my eigenstate? And we know that this is going to be the product of the solution of the three different Hamiltonian, because we can do separation of variable. Okay? So the separation of variable comes directly from the fact that the three Hamiltonian can be separated, and we end up with this differential equation, which can be solved, of course, independently this way by putting all the different component x, y, and z together. And we end up with those three equations that we need to solve. And again, this is just essentially a repeat of what I showed before, but in this case in the x, y, and z representation, right? I replace px by h bar over I, first derivative d over dx, and so on and so forth. Okay? So each component, of course, corresponds to a one-dimensional harmonic oscillator. So we find that the total solution will be just the product of three one-dimensional oscillators. Okay, good. So that's something that we've done. We looked at that before. We look at a Hermite polynomial in Cartesian coordinates. What's actually very interesting about this problem is that we can also solve it exactly using spherical coordinates. Because remember, we have a spherically symmetric potential for the harmonic oscillator in 3 dimensions. So we can actually also solve it in spherical coordinates. And if we do this, we are going to learn something complementary to what we have learned so far. Okay, so let's use all the equations that we have established so far, and we will apply those for a particular potential, which is harmonic oscillator potential, which only depends on r square. So what we already know for the wave function in r representation, and in this case in spherical coordinates representation, is that it's the product of the spherical harmonics times a radial function r. And the radial function r is usually written u r over r. And so what we need to do here, because we have a spherically symmetric potential, we only have to solve for u, because we already know that the angular dependence will be the spherical harmonics. This is what all the spherically symmetric potential will give you, a two-body interaction at least. Okay, so we end up with this equation for the radial wave function. Nothing really crazy, something that we have seen already maybe 20 times. The only difference from what we've seen before is that the potential energy now depends on r square, omega square r square. This is essentially saying simply that the harmonic oscillator behaves, the interaction depends on the distance from the origin, which is of course given by the coordinates r in spherical coordinates. We can simplify this problem somewhat by introducing dimensionless variable rho and lambda. And then when we introduce rho and lambda, we end up with the equation in the blue box, which is exactly equivalent from the equation in the red box, but just a little bit simplified because all the constants were factored into the new variables that we have here. Okay, so now we are going to use a very similar approach as we've used in the hydrogen atom, and the solution is to look at the solution far away from the origin, and so we are going to look at the solution far away from the origin, and we're also going to use a solution close to the origin that we have already established, right? Remember that the solution close to the origin we have established as u depends on the rho to L plus 1. So if you do not remember, go back to section 10.1 of this screencast. This is where we established that fact that the solution close to the origin should be rho to the power L plus 1. Now we can also do the same for the solution very far from the origin. And in that case, we find that the equation to solve is the equation of second derivative of u is equal to rho square u, which has for solution either the exponential e minus rho square over 2 or e plus rho square over 2. We know that e rho square over 2 is not acceptable for normalization purposes. So that means that at the end of the day, we have a solution that looks like the one that's provided there, with function f, which we don't know what it is. That's what we still need to establish. And we are going to suppose it looks like a series, okay? A power series in terms of rho. I'm not going to detail this in the screencast. This is something that we do as an exercise, and it's a very important exercise, actually. It's not a trivial exercise. This is one you should do carefully. When this course is taught in real life, we actually provide this solution in detail during recitation. The point is, when you solve this equation, when you introduce this f of rho inside the equation, you realize that the that solution behaves as rho to the power rho square, as e to the power rho square. Therefore, it yields a full solution u that is not normalizable. Therefore, that series is not acceptable. In other words, the only way to make it acceptable is that series has to terminate. In other words, it has to be a polynomial, not a series. And that termination of the series imposes the value of ck, and then actually imposes the value of lambda, and in turn gives you the value of the energy. It actually gives you the quantization of the energy. So this is not something trivial. It takes 2 or 3 pages of calculations, and I actually invite you to do it. But what we find at the end of the day is that the energy, the quantization for the energy of the oscillator in spherical coordinates will be given by 2nr plus L plus 3/2 times h bar omega. nr will be the number of nodes in the function f. In other words, will be the order of the function f. L, of course, is as always the eigen is related to the eigen's value of L square operator, and that means that we can write 2nr plus L as a number n, and then we end up with, of course, with the same solution as we've done before for when we solve the three-dimensional harmonic oscillator in Cartesian coordinates. We find it n plus 3/2 h bar omega. However, we found something slightly different. This is another view. I mean, this is of course compatible, but this is another view. Remember, the n value when we use Cartesian coordinates was related to the sum of nx, ny, and nz, so the number of oscillator in the different directions. Here it's a little bit different because we're in spherical coordinates. N is equal to actually 2nr plus L, nr being the order of the function of the polynomial, and L being, as I said, related to the eigenvalue of the L square operator, right? The eigenvalue of the L square operator is L times L plus 1 times h bar square. So you see those two things have to be compatible, and we can check that. In fact, we can check that for the degeneracy first by looking a little bit further into this degeneracy that we have for this case. If L equals 0, the degeneracy, of course, is just 1. If L equal 1, we have larger degeneracy, and so on and so forth. So you see, this is the different possibilities of realizing a number L, a number n. So for example, n equals 0, we can only realize it by L equals 0 and nr equals 0. So we have only one, we don't have the degeneracy. For n equal 1, we can only realize n equal 1 if L equal 1 and nr equals 0, so there is no degeneracy either. If n equal 2, now this is starting to be different. We can realize n equal 2 two ways, by having nr equal 0 and L equal 2, or nr equal 1 and L equal 0, and so on and so forth. So we increase the degeneracy, but the degeneracy here is understood in terms of L values and in terms of the order of the polynomial, instead of what we found from the number of oscillator in the x, y, and z direction. And in fact, this table here shows you the one-to-one correspondence between the Cartesian coordinates and spherical coordinates. And you see that the degeneracy in both cases, of course, is the same, which makes sense because this is solving the same problem, really. So what I suggest to do here at this point is to pause the screencast, take a piece of paper, and convince yourself that you can go from the left to the right. And the best way for you to do that is to, once you think you have understood this, try to work it out for n equal 3 states. And you will find all the possibility of creating n equal 3, either using n, x, and y, and z, or using 2nr plus L, as we've done here. So this is a very nice example of a problem that can be solved two different ways. And you see that this complementary views of the properties of the states is quite interesting, because you do not learn the same thing from the two states. Okay? So you can, of course, show that there is a one-to-one correspondence. The best way to look at it is to look at the ground state. In fact, the ground state is nx equals 0, ny equals 0, and z equals 0, which, of course, we remember this is the product of three Gaussian. Okay? So the product of three Gaussians is going to give me a Gaussian as well. Okay? And that should correspond to an L equals 0 state, and this is actually exactly what we find. This is an L equals 0 state. There is no angular dependence, so it's a spherically symmetric state, and this is exactly what we would expect for an R equal 0 and L equal 0, which is exactly what we have here. And of course, we can look at excited state, for example, the one that corresponds to one quantum along the x direction, so nx equal 1, ny 0, and sz 0. And when we do this, we end up with a Gaussian, there's something that looks like a Gaussian times x, and we can replace x by r sine theta cos phi. Of course, this is just spherical coordinates going from Cartesian coordinate to spherical coordinates. And we do see indeed that this is an L equal 1 state, and that's actually giving, and this is an R equals 0. Yeah, this is what we see. This is a combination of the two spherically harmonic state, as we would spherically harmonic function 1 1 and 1 minus 1, as we could have anticipated from a symmetry standpoint. Now, I'd like to say one last thing before I finish this chapter. This is a long chapter. This is a difficult chapter, but this is one where we actually essentially put everything together we've learned so far. The high degrees of the degeneracy is reminiscent of the hydrogen atom. We see there is a lot of degeneracy of the harmonic oscillator, and we could understand the degeneracy in terms of m values. We have a spherically symmetric system, therefore, for any given L, since we have 2L plus 1 m possible values, we understand that degeneracy. What we do understand less is why different values of L's, which after all give a different centrifugal barrier, why different values of L's would give the same energy. This is what people call usually the accidental, an accidental degeneracy. But in fact, it's not really accidental. It is due to another conservation law. And the conservation law is actually very interesting, is to show that in fact, if you look at a 1 over r potential, like a gravitational potential or electrostatic potential, or even an r square potential, like a harmonic oscillator, there is something very interesting about those, that the fact that there is, in fact, this is the only potential that yield closed trajectories. So you have an elliptical trajectory, for example, think about the Earth around the Sun. It creates a closed trajectory. But most of the time, if you were to try to numerically solve a problem which is not exactly 1 over r for the potential, like for example in general relativity, you will find that the trajectory does not actually close. This is called the precession of the perihelion, for example. This would be a solution of general relativity where the potential is no longer precisely 1 over r. So what we have in this case, we have actually a conservation law. And the conservation law is the fact that you close the trajectory, means that in fact what the conservation law you have is this fact that the position of the perihelion is conserved. So the fact that we have a conservation law is related to the fact that we have degeneracy, as we have seen before. So this is what is explained here. So the perihelion and perigee, apogee, and so on and so forth. That means that the position of the orbit is conserved. So this is not exactly accidental. This is really there is a mathematical reason for this, which is related to the specific, the specific shape of the potential. That also means that if you have a potential that's not so simple as 1 over r or r square, you're going to have a much more complicated trajectory, which means a much more complicated spectrum, and with much less degeneracy, less symmetry, if you wish. This slide concludes this screencast on chapter 10. I strongly encourage you to do the problem at the end of the chapter. I also encourage you to go back and make sure you understand what's going on. Finally, one thing that you probably have learned from this chapter is that we have solved the same equation all the time. We have used the same tricks all the time. We have essentially repeated the same tricks all the time, but there are a number of concepts that you need to know. For instance, you need to know that we have to understand the behavior of the wave function close to the origin. We have to understand the behavior of the wave function far from the origin. We have to understand what's going on at the interface, for example, when we have a finite well of an infinite well. When we understand those concepts and we put them at works, we actually find that solving those problems is not really complicated once we have a good grasp of what equation we try to solve. I strongly encourage you to spend time to review this and to seek help and office hours or otherwise by email as needed. Thank you very much.